So our first topic for today, recursion. Anybody know what it is? You don't have to put the definition. I'm just curious to see if you guys know. Just, put in the chat if you know what it is. Have you studied it before in your program? A little bit. Recursion always reminds me of that one episode of The Simpsons. It's an oldie because only the oldies are good. But they're at the end, they're all digging a hole looking for a treasure, and they're just digging deeper and deeper. And then the one guy says, "How are we going to get out of here?" And the other guy's like, "Dig up, stupid." And that's what I think of when I write recursive methods, is you got to dig up, which doesn't always make a ton of sense, but that's kind of how recursion works, is you get yourself deeper and deeper and deeper into a hole, but you have to make sure that there's a way that you can climb out. Otherwise, you just end up stuck in an infinite recursive loop. So that's not what we want, right? We want to be able to dig up eventually. So the term recursive, it technically just means something that reflects on itself. So like a mirror, or if you put a mirror in front of you and a mirror behind you, and you can see that the image repeats and repeats like a million times. If you look to the side, you can see like infinite amounts of U's reflected there. Because mirror A reflects mirror B, and mirror B reflects mirror C, and whatnot. So we have this term recursion in programming. We mean a way of repeating an algorithm. Sometimes we also say that self-referential classes are recursive because the application of that class depends on the same instance, or rather on a different instance of the same object type. So a recursive class, if you hear that term, it just means an object that refers to or contains other objects of the same type. I tend to call those things self-referential, but the terms can be used interchangeably. So when we wrote our classes that represented an item in a linked list, those classes could be termed recursive because you had an item, and then you also had within it a pointer to the next item. But today we're going to look at recursion as a way of repeating an algorithm. So in the past, we've kind of focused on loops as ways of repeating. That's how we teach it to you when you first start in term one, is like you want to repeat something, you write a loop, a for loop, a while loop, or whatever. So traditional iteration using loops is kind of trapping you within one structure that repeats until some ending condition. So we have for each, while. If you write a do while loop, all of those pretty much follow the same rules, where you need some kind of start condition, a continue condition, true or false, and a way to move or iterate. If you have a counted loop, like a for loop, then it's done via that loop counter variable. If you have a while loop, you have some kind of conditional value that is either true or false, but we know that if the value starts out as true, it has to eventually become false so that you have an exit. So what I'm trying to get at here is every loop has to have an exit strategy. And recursion is the same. The exit strategy is the most important part of it. Otherwise, you just get stuck forever. Now, the one main difference between iteration and recursion is that when you're using iteration, the problem never changes. You're doing the exact same thing over and over and over until some counter or condition is reached. But when you're using recursion, the goal is to make the problem a little bit smaller each time until you finally get to the smallest possible outcome. Now, a lot of people struggle with recursion. I know I did when I first learned about it. So if you find it a bit of a confusing topic and you find that you're just getting stuck in a lot of loops, that's normal. So I wanted to, predate this lesson with that little caveat that, yeah, it's complex. It's conceptually different from iteration, which we are most used to. So let's take a look here. One of the common recursive techniques, it's not the only one, but it's the one we're going to study today, is to create a function that calls itself. So there's that reflection of yourself again, right, that I mentioned earlier. That recursive means that a method is going to call that same method. So just like in any repetitive algorithm, we need to hit those same 3 points: the starting point, the way to advance, and the ending point. But recursive algorithms work like a stack. So we talked about stacks ages ago. I think it was like week 2 or 3, where we learned about all the different types of data structures that we're going to study. And the stack is the one that is first in, last out. So you put one element on, and before you can complete this, you put the next element on, and then they end up piling up. And when you get to the point where there's nothing else to do, then you start completing elements, but you complete them in reverse order. So you would complete 4, 3, 2, and then 1 is the last one to get completed. So that's the way that recursive algorithms work. You provide a problem that you can't solve, but you can break down. And then you try to solve the broken down piece. And that might be a problem that you can't solve, but you can break that down. And then you try to solve that broken down piece, and so on and so forth, until you get to a point where you can't break it down any farther. It's the simplest problem. So you provide a solution to that simple problem. And then that problem gets returned to where it was called from. And now that you have a solution there, you can solve the problem above it. And then that solution gets passed back to where it was called from. So you end up drilling down, 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 and then back up, up, up. So we're going to practice solving this. What is the value of b to the power of n for positive integer values of b and n? So we're going to keep it simple, no negatives, no decimals, just integers, positive integers greater than 0. So we want to solve exponents, essentially. What does 2 to the power of 3 equal, or 5 to the power of 4? So we're going to solve 2 to the power of 3. How do we solve it? Well, we have to consider, how we're going to solve this algorithm. So for any exponent number, I think, we learned the solution quite some time ago. We know that this is 2 times 2 times 2. And we know that this one is 5 times 5 times 5 times 5. So you take the base and you multiply it by itself, exponent number of times. So this is an easy problem to solve with a loop, right? You run a loop that runs n number of times, and for every loop iteration, multiply by b. Easy loop solution. But what about solving it recursively? I said we wanted to break it down into smaller problems. So here's an example of doing that. If we break 2 to the power of 3 down into smaller problems, 2 to the power of 3 is also equal to 2 times 2 to the power of 2. Agree? So that is breaking it down into one smaller step. Now on this side, this is something that I can solve. Multiply something by 2. But on this side, we have another exponent. So I'm going to take this exponent and break it down. So now on this side, we have 2 times, which is something I can solve. But over here, we have something that's still a bit complex. So we're going to break this down. 2 to the power of 1 is the same as 2 times 2 to the power of 0. Now, this obviously, the 2 times, that's something easy to solve. But now over here, I've gotten to a point where this problem can't get any smaller. 2 to the power of 0. Anybody know what 2 to the power of 0 is? Right. And over here, obviously, I gave the answer away. It's in this cloud. So anything to the power of 0 is 1, as long as that number is positive. So 9 million to the power of 0 is also 1. So if we have the smallest possible answer, which is anything, whatever the base is, by the time we get down to 0, the problem becomes trivial. This thing is always 1. But now that I have the 1, now I can finish this problem because it's just 2 times 1. And that's 2. So the 2, this thing, makes it so that now I can finish this problem. It's 2 times 2. Great. Solve that, and it's 4. But now that I have a 4 returned up here, now I can solve this problem. It's 2 times 4, which is 8. And 2 to the 3 is 8. So the algorithm that I wrote at the bottom here, we continue to calculate for b to the power of n, b times b to the power of n minus 1. And we just keep on doing that until we get to 0 up here. So the goal of any good recursive algorithm does 2 things. It makes the problem smaller, and it has a simple, easy, minimal-sized endpoint where you can't make the problem any smaller, and then you've reached a solution. So why do we stop at 0? We stop there because it's the same for any value of b. So there's nothing else to solve. It's not solving a difficult problem if the answer is the same every single time. So for every value of b, multiplying a number by 1 doesn't change its value, no matter what the number is. So if we end up with 2 times 2 times 2 times 1, the 1 isn't going to affect our outcome in this particular algorithm. So we can stop calculating when we get to that point. We don't want to go any smaller than 0 there. So let's take a look at the method. I called the exponent method with b for the base and n for the exponent value. And we have a simple if-else here. It says if n is greater than 0, do something, and otherwise return 1. So if we look at the inputs, b and n, we're looking for values of b. We already said that b has to be an integer greater than 0, and we want n to be an integer greater than 0 as well. So if I calculate, for example, 2 to the power of 3, b is 2, n is 3. So we're saying if n is greater than 0, which it is, we're going to return b times the exponent of b to the n minus 1. So on our first iteration, we're saying return 2 times 2 to the power of 2. But we can't return it yet because we have to solve this first. So we end up calling this function again. But now we're calling it with 2 and 2 because we're trying to solve this piece. So when we call 2 and 2, we still get in the if statement. we're still trying to return b times exponent of b n minus 1. But now for this, we're trying to return 2 times 2 to the 1. Because n was 2, we're passing n minus 1. So the problem's getting smaller. N is decreasing on every nested call. So I'm trying to now solve this call. So when we get in here a third time, now keep in mind the first one hasn't even returned anything yet, because we can't solve the first one until we solve the second one, and we can't solve the second one until we solve the third one. This is why it acts like a stack. So if we get in here with 2 to the power of 1, we're going to try returning, oh, I've lost my pointer, here we go. This is a lot easier when I can do it on the whiteboard. So here we're trying to return 2 times 2 to the 0. But we have to call the exponent function again to try to return this. So now we're in our fourth call, where we pass 2 and 0. But in this case, when we get a 0, we're getting into the else branch. And the else branch just says return 1. If your exponent's 0, the answer is 1 always. So now is when we can try to dig up. I'm going to change my color here. So if 2 to the 0 returns 1, that means this thing is a 1. Now we're doing 2 times 1. Well, 2 times 1 is 2. So we return this whole thing as 2. Now we can solve this problem, 2 times 2. That whole thing is 4, so we send back the 4. Now for this main one, we can do 2 times 4, which is 8. So the final value that gets returned after returning 1 and then 2 and then 4, then it becomes 8, and 8 becomes the final solution. So we can drop this code into our Visual Studio project. Let me just open it up here. I'm going to copy my method from the slide, and we'll put it in here. Probably could just type it faster than copying and pasting at this point. There we go. So if we want to, we can put a breakpoint and step through, when we call it. I'm just going to keep my console window open with a read line. So when we get into that exponent method, actually I'm going to put my breakpoint here, not there. If I call this method, we can watch it step in over and over and over again. Eventually. There we go. I think I've got my debugging windows closed. So we've got b is 2 and n is 3. As we continue through, we're into exponent at the next level. You can see how it calls it again for different values of b and n. So we can see how n is decreasing on each time. But as we continue to step through, eventually when n is 0, we get down here, and then we can watch all the returns happen. So we return 1, and then we can see how exponent returned 1 on the first iteration. That was when n is 0. And then we continue from there, and then we end up back here. The next one returned a 2. And then we're returning the next level from there, which is a 4. And then finally we will return the 8 to the main call. So our result is going to get the value 8, and then it's going to go onto the screen. Now there's some more slides in the slideshow that step us through this process. I tried to use colors to indicate the different calls. So now here's our challenge to see if you can make something similar. The challenge is to build a pyramid in the console output without using any fancy alignment techniques, just using white spaces and stars. So the pyramid properties, it has a height, so the number of lines, as input by the user. So this is a pyramid of height 5, because there's 5 lines, right? 1, 2, 3, 4, 5. The first line always has 1 star in the center. The number of stars increases by 2 per line. So the number of stars is always 1 on line 1. And then if you have a line 2, it's going to be 3 stars, and then 5, 7, 9, etc. It's going to be padded by spaces on the end. I actually took the underscores out of this example, but this line at the bottom is 9 stars. The line above it is 7 stars with a white space on either side. This one is 5 stars with 2 white spaces on either side. So the idea here, you'll notice every line should be the same length. That is the hint that I'm going to give. The final line should have no spaces on the ends. And the length of every line, so the number of characters output, is always height times 2 minus 1. So you see if the height is 5, 5 times 2 is 10, minus 1 is 9. There's 9 stars on the last line. So see if you can write a recursive function that can produce something like this, where you can call, a write line method maybe, or something like that, whatever you choose to name it, that writes the line and then calls itself to write the next one. Usually I do this as an in-class exercise, but I'm going to pose it to you now, and we're going to move on away from it. I'm not going to sit here for the next half an hour and hope that somebody somewhere is working on this. So we're going to move on in our lessons, but I do want you to try to give this a shot if you can. And if we have time at the end, we can take up some solutions to this project. Or maybe I'll make a video outlining a possible solution to this project.